Okay, so in the last class we have discussed partial derivatives of higher order orders. Okay, partial derivatives of higher order. That was then. Okay, then we have discussed the chain rules. If z equals to f of x on y, and if x is a function of phi of t and y is a function of psi of t, one parameter family, then we have seen that z dt can be written as del z del x dx dt plus del z del y then dy dt. So that is one chain rule. Third thing we have seen, if we have this type of function where x and y are functions of u comma v, phi of and psi of where u comma v. So one practical example we have seen, that is the GDP of one country is a function of this type of function essentially. Okay. Now for there we have calculated del z del u, but it is but we could not but we have not discussed there that what will be the actual value of del z del x, the partial derivative with respect to x, or del f del x. What is the value? Similarly, here also we have not discussed the partial derivative with respect to y. So today we are going to find out this value with the help of one new entry, which is called Jacobian. Okay. Now, but before I go forward, let me just show you one example that where del 2 f and del these are not equal. They are not always equal. That is fxy not equals to fyx. Under which conditions they will be equal, that we will use one theorem. But in general, they are not equal. In some particular examples, they are equal. So I will show you one example where these two mixed partial derivatives are not equal. So for this example, if we consider this one, this function, suppose f of xy is defined by this function. Okay, then it is well defined since we have included the value at 0, 0, at 0, 0. we have included. So by definition, if we differentiate with respect to x, partial derivative with respect to x, then this is done for when x, y are non-zero. So we are actually differentiating this function with respect to x. So if we do that, so this will become this. And if we simplify, then we will get this value. Similarly, if we differentiate this value with respect to y, then we will get this one and this one after simplification. Next, what we have to show, because if we want to find out the the derivative of this one, del z del y, then we must show this one is continuous, right? The inside function should be continuous. Otherwise, we cannot do the differentiation, because if it is continuous, then only differentiation we can do the differentiation. Otherwise, not. So we must check whether this inside function, is continuous or not. Okay. For that, we have to check the value of this function at 0, 0, at 0, comma 0. So del f del x, that is fx. Okay, at 0, 0 is 0. So similarly, this one is again 0. So again, the functions are actually the first order partial derivatives. This is del z del x, and this is del z del y. So both of them are functions of x and y, and they are continuous also and well defined, because 0 is included. So both are continuous. So next, what we need to do, we need to calculate the mixed partial derivatives. Okay. So if we do that, the mixed partial derivatives. Okay. So by definition, mixed partial derivatives will be this one. The first one, let us consider about the first one. Del f del x. This is del z del y. Okay. Then by limiting definition, we have to do this. Okay, limit this is actually del x fy. So this is nothing but limit, okay, just equal that this is h goes to 0. So if you just recall the definition of partial derivative with respect to x, what was that? Del z del x, limit h goes to 0, f of x plus h, f of y, f of x comma y. Okay, so the same definition we are using here. So this one will be like f of y. Here the function is y, f of y, f suffix y. So h 0 at the point 0, 0. Since we are particularly considering at all other points it will be differentiable. So we just need to verify at the point 0, 0 whether it is true or not. So here it is f of y 0, comma 0. Okay, so this one will become 1. Similarly, the other mixed partial derivative will be -1 at this point. So if both these functions are not equal, okay, f of xy and f fyx. These mixed partial derivatives, in general, they are not equal. But under which condition they will be equal, that is given by the next theorem. It is called Clairaut's theorem. So if the partial derivatives are exist and continuous also, then this mixed partial derivatives will be equal. Okay. So that means we have to consider this function after this derivative, okay, del z del y and del y del z del x, both should be continuous. First of all, they will exist. Okay. The limits should be the limits. This limit should exist. Okay, this limit should exist. Okay, first criteria. Exist. Then they are continuous. That means if they're continuous, then the functional value, once they are continuous, this will imply they will be well defined at that point. Well defined. Then second criteria is the limit will exist. That is again first one is satisfied. And third is the functional value, the limit value equals to the function value. Okay, so the limit value and the functional value. So in that situation, this mixed partial derivatives at that point will be equal. So this is given by Clairaut's theorem. As usual, this proof of this theorem is not part of our syllabus. It's just for our information. So this is what actually I missed in the last class, and we have defined this total differentiation in the last class. So let us come back to our today's discussion. That was that how to get this one is over now. Okay. So in the last class we have seen how to find this one. These values we have calculated. We have calculated these values. Now, with the help of these values, we have to find out the partial derivative with respect to x and y. Because the function is given as this one, where x and y are functions of uv. We don't want the partial derivatives. Okay. If it is asked, then find this value, then we will do it. But if it is asked to find out this value, okay, then we'll go for chain rule. So let us move forward and define a new quantity that is called Jacobian. So what is a Jacobian? So let us find out here. So how do we get this? Jacobian, J is denoted by J. It is very useful. This will be very, very useful while we study ordinary differential equation, then minima, maxima of several variables. Minimum, maximum of function of several variables. It has numerous applications in mathematics, in engineering also. So this Jacobian, we have to learn it very, very carefully. So this is actually defined by, okay, the J is defined by this one. So tell x, y, depending on the variable. yp ub. This is the determinant of del x, del u, del x, del v, del y, del u, del y, del v. Note that this is a very easy to remember this expression of this j. It is a determinant. So the numerator, in the numerator, x and y are the variables. So x1 will be there. Okay. In the denominator, y and u and v are there. So partial derivative with respect to, so del u and del v will be there. So similarly, in the first row x1, in the first row x will be there. In the second row y will come. But the denominator will always give u and v. Okay, here also denominator. So this is just a. So how this formula is coming? How do we get this formula? So this is actually using the Cramer's rule. From these two equations, here what we are getting, if we just do it, okay. So we want to determine these values. F of x1, so del f del f1, del f del x. So let us call it x1. Okay, this one, suppose we call it x1, and this is x2. So what we are having here, x1 into del x del u plus x2 into del y del u. This is equals to del f del u. Similarly, this one is x1 into del x del v plus x2 into del y del v del f del v. Okay. So if we just use the Cramer's rule x1 and x2, then we will get this values, this expression, and the determinant of this one is known as the Jacobian of the variables of the transformation. Note that z is a function of x and y, and x was function of phi of u, p, y is also function of u and p. Okay. So from here, what we get, if we calculate, this is j of xy, j of xy, ub, del of xy by del of ub. So we will write it. Okay. So from that equation, from this equation, we are having this one as, okay, we are writing it as j. Okay. Now by definition, we have del of xy, xy UP. Del of UP is nothing but del of x by del u, del of x by del v, and del y by del u. Similarly, del y by del v. So if we try, in place of this one, in place of x, we are substituting f. So this one will be del of y. This is del of u v. This is nothing but del f, del u, del f, del v, then del y, del u, del y, del v. Okay. Similarly, we can define this one. Okay. Okay. So from here, we can see that we have to find out this x variable. X1 is this one. In terms of the partial derivative of f with respect to x. So this one is nothing but 1 by j, that is 1 by Jacobian, into this one, the new term that we are defining. Okay. This will be clear if we discuss one example. Similarly, the other term, the partial derivative with respect to y, will be calculated as minus 1 by j into the Jacobian of this one, del x, and these are actually formula which comes from the previous slide. So this is u. Similarly, we can define for 3 variable case also. So if we have u, v, w, our functions, ax is a function of u, v, w, y is also a function of u, v, w, z is also a function of u, v, w, then we can define the Jacobian of 3 variables with respect to x, y, and z. This will be del u, del x. Whoever is in the numerator, they will come in the numerator. Whoever in the denominator, we have to for partial differentiation with respect to them, x, y, and z. Okay. So for this case also, we can define. Okay, we can find the partial derivative with respect to x. These are actually not t, these are actually tail. This is also t, this is also tail. A typing mistake. So this one will be, this is just like similar to the Cramer's rule. So 1 by Jacobian, 1 by j into whichever we are trying to find out with respect to x. So in place of x, we will substitute this value, f. This f. Similarly, we want to find the derivative with respect to y. So in place of y, we will substitute f and do the evaluation. Similarly, finally, in place of z, we will substitute this. Okay, so this is supposed to be w. This is x, y, and z. Actually, this is supposed to be u. Okay. Actually, they wanted to avoid in the last row. Oh, this is actually okay. Same as writing this one. Where Jacobian we already have calculated in the previous step. This one is, let's tell you, UPW XYZ. XYZ UPW. Okay. So with this formula, we will go to find out the next expressions. So here Z is one given function is there. Z is a function of x and y, where x is a function of r comma theta, cos theta, y is a function of r sin theta. So let us call it phi of r theta. Okay, so this is psi of r theta. Okay, so here we will use the these formulas. So we have to calculate this one and this one also. After that, we have to take the squares. Then we have to find out whether we are getting this one or not. So we have to find out del f del y fx uv. Okay. So for this one, we will find out del f del x, which is 1 by j into del of, what was that? Fy uv. Fy and del of uv means r theta. Okay. So similarly, del f del y minus 1 by j, I have to calculate. Del of, this is xf divided by del of r comma theta. Let me check whether we have written correctly. Sorry, this is fx. F and x. Let us write fx. We are keeping f in the first row actually. And that is why we are writing in this way. So let us calculate. What will be j? Jacobian will be del of this one, xy uv. R comma theta. So here it is. Let us calculate. So this is del x, del u means del r, del x, del theta, similarly del y, del r, del y, del theta. Okay, so now if you would differentiate this one with respect to r, dx, del x, del r. So this will become, what is it, r1. So this will become only cos theta. Similarly, del x, del theta will be negative r sine theta. Okay. Now this one, if we differentiate this, del y, del r will be sine theta. Again, if we differentiate del r, del y, del theta, we'll get r cos theta. Okay. Now, if we evaluate this determinant, then j will be is r into cos square theta, r into cos square theta plus, okay, sorry, minus of negative of this minus r sine theta. Minus and minus will get plus. So this is from here we get, okay, this is equals to r. J equals to r. That is our observation. That J equals to r. Okay. Since here, from here we will get sin square theta plus cos square theta equals to 1. So this becomes r. Okay, now we have to calculate this one. So let us try to calculate. Okay, so that was our now let us calculate this one. Del f, this is j, this is negative j. Okay. So we'll calculate this inside term. This is del f del y by del r theta. This is del f del r del f del theta del y del r del y del theta. Okay. So for here we have seen that y equals to r sine theta, del y del r equals to sine theta, del y del theta, r cos theta. Similarly, x equals to r cos theta. So here we will get del x del r equals to cos theta, and del x del theta equals to minus r sin theta. Okay, let us substitute those values. So del f del r del f del theta. In place of this, we can substitute this value, sin theta. Here, for this, we will substitute this one, r cos theta. Okay, let us evaluate this value. Then what will happen? R cos theta into del f del r minus sin theta del f del theta. Similarly, del f, this term, we have to calculate this term, del f x, del r comma theta. So this one will give us del f, del r, del f, del theta, del x, del r, and del x, del theta. Okay, so this is nothing but del f, del r, and del f, del theta. And in place of this one, we'll substitute cos theta, this one. And here it is negative r sin theta. So and after evaluating, we will get here. So this one will become minus r sin theta del f del r plus no, it is negative again, minus cos theta into del f del r. So del theta. This one. Okay, for this. So with these values, we'll try to find out whatever is asked to calculate. So we have to calculate this one. Del f del x whole square plus del f del y whole square. Okay, let us calculate. Del f del x. This is 1 by j into del f del y into del r theta. So j equals to, we have calculated 1 by r. J equals to r, so this is 1 by r. And this one is negative r sin theta by del f del r minus cos theta into del f del theta. Okay, this one. Okay. Similarly, we have to calculate del f del y 1 by j into del f del x, then del r del theta, that is 1 by r, j equals to r, this is r cos theta del f del r minus sin theta into del f del theta. Okay, this part. R cos theta into del f del r, this one. Okay. Okay, fine. So if we do the simplification, this r and r will get cancelled. Just multiply this r, and r will get cancelled. If I remove this, then we will have r sin theta equals to 1 by r cos theta. Similarly, r will get cancelled. Here it will be 1 by r. Okay. Now if we take the square, and take the addition. So take the square, take the addition. Then what will happen? So del f, del x, okay, plus, so sine square theta y plus cos square theta into this one, del f, del, del f, del r, okay, plus this one, 1 by r square into cos square theta plus sine square theta into del f, del theta square plus some more terms will be there. What are those terms? 2 sine theta. Okay, negative is there, so negative. Negative sine theta 1 by r del f del r 2ab. B is here this one, 1 by r cos theta del f del theta minus, for this one again we will have minus 2 into cos theta into del f del r into 1 by r sin theta into del f del theta. Let us try to simplify it. Okay, so for here we'll get, okay, so this will become 1, again this will become 1. So let us write down. So, okay, from the first two terms we'll get as this one, del f del r whole square plus 1 by r square into del f del theta square. Okay, this one our target. Now how about this? How to evaluate? How to, this one should be 0. So that is actually the desired term we have already found, but we have to vanish. We have to check whether this one is 0 or not. So let us do it. So this one is 2 sin theta del f del theta. So this one will become minus 2 by r sin theta cos theta, 2 sin theta cos theta is cos 2 theta. Okay, then this is del f del theta. Let us write the del f del r del f del theta 2 by r sin theta cos theta del f del r to del I think it is supposed to be get cancelled. Anyway, yeah, let me check where I have gone wrong. But this part is actually negative of this one. Okay, so this one is actually positive. It will be positive. Since negative is already there, so after calculating this one, we had. Okay, now I get it. So this one is after calculating this determinant, but the actual value of this one, of this expression, this del f del y, will be positive of this one. Okay. Here it is. I have written here negative. This one is negative. So negative, after this will be actually positive. Negative plus. Okay. So this will directly get cancelled. Okay. This one will become negative and this one will become positive. This one and this one will get cancelled. So only this term will be there. So this is what we need to show. It's proved. We have to be careful about the negative sign while substituting the values of this one, del f and del y. Okay. So in this way, we'll use the idea of Jacobian to find out some more examples. So for this is example 3. If we have 3 variable case, if we are having 3 variable case, u is a function of, u is a function of x, y, z, x is a function of r sine theta cos theta. Sorry, sine theta cos phi. Okay, so here is actually x is a function of suppose phi of this is r theta and phi. Oh, sorry, phi is already there. So let me write here. F is a function of some. F is already there. So let us write g here. Y is a function of h r theta phi, and z is a function of, let us say, k r theta and phi. So what we need to do? We need to calculate the Jacobian first. The Jacobian first. After that, we need to calculate each and every term so that we can find out the partial derivative with respect to x, with respect to y, and with respect to z. Once we get it, so we'll substitute those values after squaring, okay, and we will try to evaluate, try to simplify the right hand side. Then we will get this one. Note that we have already found this part. Okay. If it is not there, in the previous example, we have already found this one. So the only extra thing is there. If we have another extra term, then for which we are getting this actually, this extra term. So you just need to verify simply. I have not shown here, so you can do it for your task. Complete this. Now for another example, it is to show that if this is j and this is called j prime, that is the inverse. Okay. There is a relation that j prime will be 1. So that is, here it is. As a property actually, Jacobian. Okay. So for the fifth example, we have to just show that Jacobian only. This is r square sine theta. Nothing complicated, just simple computations. But we have to be careful about the negative signs. Negative signs. Then only it is just a couple of expressions. Okay. So this is one example, one more example. You can take it as a task. Just let us do it for a 3 variable case. So we have to show this is equals to 4. So y1. So the Jacobian will be L of y1, y2, and y3 divided by x1, x2, and x3. So here y1 is given as, so the Jacobian will be given by this one. Del y1, del x1, del y1, del x2, del y1, del x3. Similarly, del y2, del x1, del y2, del x2, del y3, sorry, y2, del x3. And finally, del y3, del x1, del y3, del x2, del y3, del x3. That is our Jacobian by definition. J is this one. So we have to show it. This is actually also 4. So let us compute each and every term. This is actually differentiate with respect to x1. So x1 is in the denominator. So this one will become minus x2, x3, x1 square. So this is with respect to x2, y1. So x2 is in the numerator. So this one will become x3 by x1. Similarly, x2 by x1. So for the second one, del y del x1, x1 is already numerator. So this is x1 will get cancelled. I mean x1 will be 1. So here it will be x3 and x2. Similarly, x1 x3 by x2 square. Similarly, with respect to 3, this is x1 x2. And this one will become x1 is already there, so this is x2 x3, x2 by x3. Next is with respect to x2, this is x1 by x3 minus x1 x2, x1 x2 by x3 square. Okay. So in the next line, we have to take x square, x1 square, x2 square, and x3 square common. So this one will become minus x1, sorry, x2, x3. Then this will become x1, x3. Next one will become x1, x2. Similarly, for the second row will become, okay, Okay, x2, x3 minus x2, sorry, x1, x3, and this is x1, x2. Third row will become x2, x3, x2, x3 minus x2, x3. So again we will take x square outside, then it becomes so the determinant becomes minus 1, 1, 1, 1, minus 1, 1, 1, 1, minus 1. So this portion will get cancelled. Numerator and the denominator, this will become 1. And this is minus 1 into 1 minus 1. Minus 1, okay, this one. Minus 1, minus 2. Minus 1, minus 1. Similarly, plus 1 into, this is, so this is 1 plus 1. Okay, so this is minus of minus 2. This is plus 2 here, so plus 2 here. This is equals to 4. So that is what we have to show. This is equals to 4. Okay. Now the properties of Jacobian. There are a few properties which are very, very important. I think most of the properties we have already discussed. The first property is this is J and J prime is 1. Second property says if U and B are functions of R and S, where R and S are functions of X and Y, then we can write the chain rule. Here it is, using the chain rule, we will get this one. Okay. Now the third property says if the functions are independent variables, the three independent variables are x, y, and z, and these are the functions. Whether the functions are note that we have seen whether a vector is independent or not. We have seen c1 b1 plus c2 b2 plus cn bn. We'll take the linear combination if all the c1, c2, and cn are equal to 0. Then we have said that these vectors are linearly independent. Okay. If at least one of the ci is non-zero, then we have said that this is actually linearly dependent. Similarly, that was for vectors. Okay, that was for vectors. So the same idea can be applied for functions. So given n functions, for example, let us suppose f1, f2, f1x, f2x, then fnx are n functions. Then c1 f1x plus c2 f2x and n fnx. We'll take the linear combination and we'll check whether they are linearly independent or not. These functions are okay. So here it is functions. Earlier we have seen vectors. So these are actually useful. This idea, linearly independent, independent functions, independent functions are useful for solutions of differential equations. Solutions of differential equations. Now, whether it is ODE or PDE does not matter. In order to find the solution of a differential equation, for example, d2y dx2, that is given xy, the solution should be y1x, okay, y equals to y1x. The idea is actually y equals to y1x, and okay, I think you have seen that c1 y1x plus c2 y2x. These functions, okay, this one and this one are actually independent. I don't think here it is linearly independent says, because these functions may not be linear. So here it is actually independent. Both of them are independent functions. They do not depend on each other. Okay. So that is what the idea. For this, we have to use the concept of third property. If they are somehow related, if these functions are somehow related, then the Jacobian will be 0. So we will see one example to verify this one. And then after this, we will come back to the converse. That is the remark. So if you think about this function, u, v, and j, w. So here x, y, and z are independent functions, independent variables. Okay, independent variable, and these are the functions u, v, and w. We have to show that these variables are functionally related. Okay, they are related. And here we do not say linearly dependent. We do not say, because that was for vectors. Linear. Here we say they are functionally related. Functionally related or dependent. Functionally related. So if they are functionally related, then this will satisfy. The Jacobian will be 0. If they are related. To find the relationship between them. Okay, after this, we have to find the relationship. So let us calculate the Jacobian. Jacobian will be this by definition. This one. Okay, u, v, w. So u is there, v is there, and w is there. And the denominator will have x, y, and z. So after calculating, we have this one. We'll evaluate this determinant. So we are getting this is a 0. Hence, the variables are related. These are related. Now we have to find out the relation between these. So as you can see here, w can be written as x times x minus u. It is u plus v equals to 2x. Or therefore, we are writing this. So this is one more property of a Jacobian. That if they are related, then we have this Jacobian as 0. From this Jacobian, we can get the relation. since this is 0. So if we evaluate with respect to this one, okay, we cannot evaluate, evaluation is 0. So how this is getting? Okay, from here it is. They are actually taking this. W is equals to x times x plus y to the x plus z minus y. Okay. And it was already there, v was already there, x plus y minus z. So sorry, this is u actually. X minus y plus z, w equals to x into u. Okay. Again, this is u plus v equals to 2x. Okay, let us add these two things. This is u and plus v. U plus v will be x plus x minus y plus z plus x minus x plus y minus z. Okay, so this one gets cancelled. It remains only 2x. Already we have that this one w equals to xe. Now we are getting u plus x equals to this one x. Okay, so 2x equals to, so from these two, so u plus v equals to 2x and w equals to xe. So from these two equations we are getting this. This is how we can find the relation between u, v and w. So these are actually your task. Answers are given. To verify, you just need to verify whether they are correct or not. So if you do not able to solve them, please let me know. I will provide the solution. Okay. So now, the one more important topic, that is called homogeneous function. A function is said to be homogeneous function in which the power of each term is actually same. So it is actually looking like a polynomial. So here it is, power is n. The joint power x and y, the joint power is n. Here also it is n. Okay. So all the power is n. So from here, if you take x to the power n outside, then it will become a polynomial in y by x. Okay, h0 this time. And this can be written as, this is a function of this phi of y by x next to the power n. So if this function can be written as in this form, then we can say that this is a homogeneous function of order n. For example, this is the definition. For example, if we have this type of function, so here it is a homogeneous function of order 3. Note that if we can write it here in the negative term also, then homogeneous function of order minus 3 by 2. So it can be negative. Here it is does not say anything about whether positive, negative, or integer. It can be fraction also. It is just any real number. It can be 0 also. But if we cannot write a function in terms of this form, x to the power n phi of y by x, or we can also write y to the power n, okay, another function of psi of it is y by x, this will be x by y. Then also it is possible to find out one homogeneous function of order n. But if we cannot write it, then this will be a non-homogeneous. I mean, we cannot say this is a homogeneous function. Some more equivalent definition of homogeneous function of degree n. So if we just substitute, suppose f of x y is given. In place of x, we'll substitute lambda x. In place of y also, we substitute lambda y. And if we think about, if we get this is lambda power n, f of xn, then also we will get the homogeneous function of. Okay. Already we have discussed this one. But if you can get f of xy equals to n, then we can write it as homogeneous function. We can say. Similarly, we can have this one, a polynomial in order in place of in x by y also, in the form of x by y. G, this is y to the power n. That is also possible. So this is actually a homogeneous equation in two variables. But homogeneous equation of three variables, if it is this kind of, then we will have to write it. All the variables, we will put lambda y, lambda x, lambda y, and lambda z. If we can find this one, then we will have these equations. Otherwise, in other words, if we can think about a function, this function can be written as x to the power n into g of y by x and z by y, z by x also. Then also we can say that this is homogeneous equation in three variable. Earlier it was two variable. Now we are talking about three variables. Okay. So for example, if you can think about this one, so this is a homogeneous equation. You can write it. Homogeneity, degree of homogeneity is 2. For this one, it is 1. For this one, it is -1. Similarly, for this one, it is -4. For the fifth one, it is -1. And for the sixth one, it is -half. Okay. These are some couple of examples. Now, there is a, this is not homogeneous. Because we cannot write it as a x to the power n into g to the power g of x by y. This function cannot be written as. Now, there is an important theorem which is known as Euler's theorem. If this function is homogeneous, f of x, y of degree n, then x and y has continuous first and second order derivatives. Also, if we have the continuous first and second order derivatives, partial derivatives, then these relations will hold. These two relations, equation 1 and equation 2, will hold. So that is Euler's theorem for partial derivatives for homogeneous functions of degree n. Okay. So what we need to do, whether the function is homogeneous or not. If it is homogeneous, then what is the degree? Okay, once we find out, then we have to verify the first order and the second order partial derivatives. And once we calculate, then from there directly we can write it. Okay. So that is one more important result in this function of several variables. The proof is very simple. Since it is homogeneous, so we can write it as this form. Just we need to calculate the partial derivatives. And just after that, we will multiply with x, multiply with y, and add them. Just simplify. After simplification, we will get this one. Similarly, for the second formula also, we have to calculate the second order partial derivatives and then simplify this one. So these are actually very simple. If you just read it carefully, you will understand it. So let us solve this problem. So whether it is homogeneous or not, we have to check. Okay, so here it is. It says that we can write this function as for all xy for greater equals to within this if xy greater than 0 and xy also less than 1 in between x is open interval we have x plus y divided by root over x plus root over y. This is less than 1. It will be satisfied. Okay. So here it is. U is defined as this one. Cosine inverse of this one. So cosine of u will be this one. Okay. Now if we take x outside, then it will become this form 1 plus y by x. So after simplification, it is become this one. So we are getting a function. This one is a function of g of y by x. Okay, so this is homogeneous equation of order half cosine of u. So by Euler's theorem, we will apply this Euler's theorem on f. Euler's theorem says x into del f del x plus y into del f del y equals to n times f. N times f. So here it is. N is our half. So n times f is our cos of u. Then x times this one and y times this one. Okay, let us just simplify. So this one will become our. Okay, this is what we need to show. Hence, it is proved. In this way, you can evaluate all the functions that is given. For example, 2, this one will become homogeneous function of degree 2. If you substitute lambda equals to lambda u equals to so lambda x, so here you are getting lambda square u. Similarly, if you substitute here lambda x, that is also possible. Otherwise, you can write it in terms of x in x to the power n g of y by x. There are two methods. Either you substitute this one in place of this x equals to lambda x and y equals to lambda x. Either you use this or try to write it in this form. So once we get the degree of homogeneity, then we can directly write the Euler's theorem, Euler's formula for the. Okay. There are two formulas. Euler's first formula. Okay, for the second formula, we have. So these are some more examples. That is worked out examples. So I will give you some task. I have to. Okay. These are actually your task to find out. Verify Euler's theorem. Use Euler's theorem to show these ones. So these are your tasks.